There is something strangely peaceful about the beginning of a poker hand. A deck is shuffled. Chips rest in quiet stacks. 2 cards are dealt face down, and suddenly, without any visible change in the room, an invisible world comes into existence. A world made not of certainty, but of possibility, of hidden patterns, silent probabilities, and decisions that must be made before the truth fully reveals itself. Poker is often mistaken for a game of luck, and on the surface, it can certainly appear that way. Cards arrive from nowhere. Fortunes rise and vanish in moments. A perfect hand can be broken by a single turn of the river. But beneath the shifting surface lies something far more structured, something almost mathematical in its stillness. Because poker is not chaos, not really. It is a system, a finite deck of 52 cards, fixed rules, measurable odds, predictable distributions. And yet, from those limited ingredients emerges a world so complex that no human mind can fully hold it all at once. Like so many of the deepest mathematical systems, poker lives inside a paradox. It is governed by logic, but experienced as uncertainty. It is built for numbers, but felt as intuition. It is a game where truth exists, but remains hidden just long enough to make every decision meaningful. And perhaps that is why poker feels so strangely human. Because life itself rarely gives us perfect information. We make choices without seeing every card. We estimate, infer, risk, retreat, and continue. We act not because we are certain, but because waiting forever is impossible. In that sense, poker is not just a card game. It is a quiet study of what it means to think inside the unknown. And before there can be bluffing, strategy, or risk, there must first be the deck itself, a small and finite object containing a nearly endless universe of possibility. At first glance, a poker hand seems almost too small to matter. Just 2 cards, 2 quiet rectangles of paper turned face down beneath your fingertips. Nothing dramatic, nothing cosmic, no sprawling board like chess, no vast field of moving parts. Just 2 hidden objects resting in silence. And yet, from those 2 cards alone, an entire mathematical universe begins to unfold. This is one of the strange beauties of poker. It takes something tiny, almost forgettable, and reveals that beneath it lies a structure of extraordinary depth. Because in poker, the beginning is never truly small. The beginning only appears small because the complexity has not yet had time to reveal itself. A standard deck contains 52 cards. That number feels manageable, familiar, finite. But the moment you begin asking how many different 2-card hands can be dealt from those 52 cards, the surface calm begins to crack. Mathematicians describe this kind of question using combinations. A combination is simply a way of choosing objects from a larger set when the order does not matter. In poker, this is important because the ace of spades and the king of hearts is the same hand whether the ace was dealt first or second. The order changes nothing. What matters is only which 2 cards you hold. So how many possible starting hands are there? The answer is 1,326. That means if you sit down and receive 2 random cards, you are being handed one outcome from 1,326 distinct possibilities. And all of strategy, all of risk, all of future drama begins from that single selection. Pause for a moment and let that settle in. 1,326 possible beginnings, all hidden inside a deck small enough to fit in one hand. This is where poker begins to feel less like a game and more like a quiet machine for generating alternate realities. Of course, not all of those 1,326 hands feel equally different to a human mind. Some are structurally similar. Pocket aces is pocket aces, whether they are the ace of hearts and ace of diamonds or the ace of clubs and ace of spades. In practical poker language, players often group hands into categories rather than treating every exact combination as entirely separate. When we do that, the number shrinks. Instead of 1,026 exact combinations, there are 169 strategic hand types in games like Texas Hold'em. That number comes from dividing hands into 3 broad forms: First, there are pairs. These are hands like 2 queens or 2 sevens. Since there are 13 ranks in the deck, from 2 through ace, there are 13 possible pairs. Then there are suited hands, where both cards share the same suit. A hand like ace and king of hearts belongs to this category. There are 78 of these suited combinations when grouped by rank. And then there are offsuit hands, where the cards do not share a suit. There are 78 of these as well. 13 plus 78 plus 78 gives 169. So depending on how you look at poker, the game begins with either 1,326 exact realities or 169 recognizable archetypes. And this is already enough to create an atmosphere of endless variation. Some hands feel heavy with promise. Pocket aces. Pocket kings. Ace kings suited. They arrive with a kind of silent gravitational pull, as though the hand itself carries authority. Other hands feel modest, almost innocent. 9 and 7 suited. 5 and 4 of clubs. Small connectors and quiet fragments of possibility. Not powerful on the surface, but rich with hidden pathways. And then there are hands that seem awkward and almost embarrassing. King and 2 offsuit. Queen and 3. Disconnected cards with no visible harmony between them. Hands that seem to whisper uncertainty from the very first moment. But poker does not only ask what a hand is, it asks what a hand can become. That is where the mathematics deepens. Because no starting hand exists in isolation, every hand is really a seed, a compressed possibility waiting for future cards to either nourish it or abandon it. A pair may remain only a pair. A weak-suited hand may bloom into a flush. 2 disconnected cards may unexpectedly collide with the board and become something powerful. A beautiful hand may die quietly. A weak hand may awaken. This is why poker feels alive. The cards are not fixed meanings. They are moving probabilities. In this way, each starting hand is less like an answer and more like a question. What are the chances this hand improves? What are the chances another hand is already stronger? What are the chances the hidden structure of the deck will unfold in your favor? Every hand is a probability cloud drifting forward through time, and what makes this so mesmerizing is that poker gives this uncertainty a physical form. You can hold it, touch it, look down at it. 2 cards, yet those 2 cards are not really objects anymore. They are compressed branches of the future. This is one of the deepest mathematical ideas hidden inside poker. Small inputs can generate vast outcomes. A tiny difference at the beginning can completely reshape everything that follows. The difference between ace-queen suited and ace-queen offsuit may seem minor to a casual eye. Just one shared suit. But mathematically, that small change transforms the hand's hidden potential. It adds flush possibilities. It alters equity. It changes how the hand behaves across countless future boards. A single detail can ripple outward into an entirely different world. And if that sounds familiar, it is because life often behaves this way too. A small beginning, a subtle variation, a tiny unseen advantage or disadvantage, and from there, entirely different futures unfold. This is why the mathematics of poker can feel strangely intimate. It does not merely describe cards. It describes the architecture of uncertainty itself. You begin with incomplete information, a finite set of hidden possibilities, and from that, you try to navigate towards something meaningful. There is also something quietly humbling in this, because no matter how experienced a player becomes, no one escapes the mathematics of the deal. No amount of intelligence can will pocket aces into existence. No amount of discipline can prevent weak hands from arriving. Every player, no matter how skilled, must begin by receiving what the deck offers. This means poker contains 2 forces from the very beginning. The first is structure. The second is surrender. You can study probabilities. You can learn hand rankings. You can understand combinations, frequencies, and strategic categories. But you cannot choose your first 2 cards. The universe speaks first, and only then do you respond. That is perhaps the quiet philosophy hidden inside possible hands. Before strategy, before dissection, before brilliance, there is always a beginning you did not choose, And yet, within that unchosen beginning, there remains astonishing room for thought, adaptation, and beauty. 2 cards. 1,326 possible combinations. 169 strategic forms. And already, from this tiny mathematical seed, a world begins to open. And soon, with the arrival of the community cards, that world will expand far beyond anything those first 2 hidden cards seem to promise. If the first 2 cards in poker are a beginning, then the board is an unfolding universe. At the start of a hand, everything is compressed. 2 hidden cards sit quietly in front of you, full of possibility but still incomplete. Their meaning is only partial. Their future is unresolved. But once the community cards begin to appear, first the flop, then the turn, then the river, the hidden mathematics of poker begins to bloom into something much larger. And it blooms very quickly. This is where poker becomes something more than probability in the simple sense. It becomes what mathematicians call a combinatorial space, a vast landscape of possible arrangements created by selecting and combining a limited number of elements. In softer language, it means this: even when the ingredients are few, the number of ways they can be arranged becomes astonishingly large. And poker is built entirely from this principle. There are only 52 cards in the deck. That sounds small. But once 2 players each receive 2 private cards, and then 5 shared community cards are revealed over time, the number of possible worlds that can emerge becomes immense. Let us begin with the flop. After your 2 whole cards are dealt, there are 50 cards remaining in the deck. From those 50, the dealer reveals 3 community cards. The number of possible 3-card flops is 19,600. That means even before the turn or river appear, there are already 19,600 different first worlds the game can enter. And that is only from your point of view. Once we account for the hidden cards your opponent might hold, and all the ways those private hands can interact with the board, the landscape becomes much larger. A single starting hand does not lead to one future. It leads to thousands upon thousands of branching realities, each one carrying its own texture, danger, and hidden logic. This is one of the reasons poker feels so strangely alive. The cards do not merely appear, they transform the structure of reality in real time. A flop of ace, king, queen feels completely different from a flop of 7, 7, 2. A board with 3 hearts creates one kind of tension. A board with connected low cards creates another. A dry board, where few draws are possible, behaves very differently from a wet board, where straights and flushes lurk just beneath the surface. To a casual observer, these are just different pictures on cardboard, but mathematically, they are different universes. Each flop creates a new topography of possibility. Certain hands become powerful, others weaken. Some hidden become powerful, others weaken. Some hidden combinations become more likely, others quietly disappear. With every revealed card, some futures collapse and others emerge. This is one of the deepest structural truths in poker. Information does not simply clarify reality. It changes the shape of it. The turn card intensifies this even further. After the flop, there are 47 unseen cards left. Any one of them can become the turn. And each turn card reshapes the board again, often in subtle but profound ways. A harmless-looking 2 may change almost nothing. A third spade may suddenly complete a flush. A paired board may create full house possibilities. A single card can redraw the emotional and mathematical atmosphere of the hand. Then comes the river, the final revealed card, the last piece of visible information, the final rearrangement of possibility before truth is forced into the open. By the time all 5 community cards have been dealt, the number of possible 5-card boards that could have emerged from the 50 unknown cards is 2,118,760. Pause there for a moment. From the simple act of revealing 5 cards from a deck, more than 2 million possible boards can arise. And that is still only the visible surface, because each of those boards interacts differently with every possible starting hand. And every starting hand interacts differently with every possible opponent range, and every opponent range changes depending on position, betting, stack size, table dynamics, and previous decisions. The result is not merely complexity, it is layered complexity. Poker does not unfold in a straight line, it unfolds like a forest growing in every direction at once. This is why even very strong players do not solve hands in the way a machine solves a simple arithmetic problem. They navigate, they estimate, they narrow, they feel their way through an impossibly large possibility space using patterns, memory, probability, and disciplined intuition. Because the full structure is too large to hold directly. This is one of the strange similarities between poker and reality itself. Life also presents us with incomplete beginnings, then reveals new information over time. And each new piece of information does not merely answer old questions, it creates new ones. A single conversation can alter a future. A single event can reshape meaning. A single turn of circumstance can transform what once seemed certain into something entirely different. Poker compresses that experience into mathematics. It lets us watch possibility becoming reality, one card at a time. There is also something almost poetic in the way poker handles revelation. The cards do not appear all at once. They arrive in stages. First 3, then 1, then 1. This pacing matters. It creates suspense, of course, but it also creates a deeper mathematical rhythm. Every stage gives the mind time to imagine what could happen next. Every stage asks the same quiet question: now that the world has changed, what remains possible? This is what makes poker so hypnotic. It is not only a game of outcomes, it is a game of transition. A hand is never simply strong or weak in the abstract. It is always becoming something. Every board is an evolving field of latent futures, waiting to either resolve or betray the hopes placed upon it. A pair on the flop may become a full house by the river. A powerful draw may vanish into nothing. A weak hand may quietly survive every wave of possibility and remain best by the end. And because of this, poker carries a peculiar emotional quality. It teaches you to live inside unfinished information, to sit inside uncertainty not as a flaw, but as the natural condition of the game. That is perhaps what combinatorial space really means beneath its mathematical language. It means the world is larger than it first appears, much larger. A deck of 52 cards does not seem infinite. And it is not infinite, technically speaking. It is finite, countable, bounded. But in practice, its unfolding complexity becomes so rich that it begins to feel almost endless. This is the paradox at the heart of poker. A small closed system gives rise to an experience of vastness. A handful of cards creates millions of visible boards, countless hidden interactions, and strategic landscapes too deep for any single mind to exhaust. And yet every hand begins so quietly. Just 2 cards. A pause. A table. A silence. Then the flop arrives, and the universe opens. There is a strange and slightly unsettling truth at the heart of poker. You can make the right decision and still lose, not just occasionally, not just ascensionally, not just in some rare dramatic exception, but regularly, calmly, repeatedly. In fact, this is one of the most fundamental features of the game. And once you truly understand that, poker begins to feel less like a card game and more like a quiet philosophical lesson disguised as mathematics. Because in most parts of ordinary life, people tend to judge decisions by outcomes. If something works, we call it smart. If it fails, we call it foolish. The mind craves neat moral arithmetic. Success means wisdom. Failure means error. But poker refuses to cooperate with that illusion. Poker separates decision quality from result, and the mathematical idea that makes this possible is something called expected value. At first, expected value sounds technical, maybe even a little cold, but beneath the formal language lies a deeply human concept. Expected value is simply the average amount you can expect to gain or lose from a decision if you could repeat that same situation again and again over a very long period of time. In softer words, it asks a beautiful question. If this moment happened forever, would this choice be good for you? That is all. Not whether this one hand wins. Not whether this one river card saves you. Not whether fortune smiles tonight. But whether, in the long run, the structure of the decision itself is sound. This is where poker becomes almost meditative. Imagine that you are facing a bet. You have a drawing hand, perhaps 4 cards to a flush, and your opponent pushes chips into the pot. You do not know what the next card will be. You cannot control it. You cannot bargain with the deck. All you can do is ask whether calling that bet is mathematically justified. If the pot is laying you a favorable price relative to your chance of improving, then the call may be correct, even if the next card misses. And if the price is poor, the call may be incorrect, even if the perfect card arrives and you win. This is one of the most disorienting lessons in all of poker. A winning result does not prove a good decision. A losing result does not prove a bad one. And that can feel almost offensive to the human mind, because the mind wants closure, it wants certainty, it wants a visible reward for doing things correctly. But expected value teaches a quieter, more mature kind of truth. It teaches that reality does not always settle its debts immediately. Sometimes the correctness of a choice can only be seen across time. To understand this more clearly, imagine a very simple situation. Suppose someone offers you a coin flip. If the coin lands heads, you win $2. If it lands tails, you lose $1. You agree to play. Now, in any single flip you might lose. The coin may land tails and you are down $1. But the decision itself was still mathematically good, because over many repeated flips, the average result would favor you. Half the time you gain $2, half the time you lose $1. On average, that leaves you ahead. That average hidden advantage is expected value. It is the quiet gravity beneath the surface of chance. Poker works the same way, except with far more complexity. Every bet, call, raise, fold, and bluff carries its own expected value. Some decisions, if repeated over many similar situations, would slowly build profit. Others would slowly bleed it away. And the player who learns to think in expected value begins to see the game differently. They stop chasing emotional certainty. They start trusting structure. This is one of the great psychological transformations poker offers. It gently trains the mind to care less about whether a single moment feels rewarding and more about whether a pattern is sound. And perhaps that is why expected value feels so philosophically rich. Because life often behaves in exactly the same way. You can be kind to someone and not be appreciated. You can work hard on something meaningful and watch it fail. You can make a wise decision and still experience pain. And yet none of that automatically means the decision was wrong. This is difficult for people to accept because we are emotional creatures living inside short-time horizons. We feel the sting of immediate outcomes much more sharply than the quiet logic of long-term truth. But expected value asks us to stretch our perspective, to become patient enough to see beyond the single hand, the single night, the single disappointment. It asks us to become friends with delayed clarity. In poker, this patience is not optional. It is essential. A player who constantly reacts to short-term results becomes unstable. They start changing good strategies after a few unlucky losses. They chase losses with bad calls. They abandon logic in search of emotional relief, and slowly, almost invisibly, they drift away from the mathematics that would have protected them. This is why expected value is not just a numerical concept, it is a discipline of perception. It teaches you to see the invisible quality of a decision even when the visible outcome is painful. There is something almost spiritual in that, to act well without immediate reward, to remain rational inside uncertainty, to trust a pattern before it pays you back. Expected value is, in some sense, the mathematics of faith. Not blind faith, not superstition, but faith in structure. Faith that if the logic is sound and the process is repeated enough times, truth will eventually emerge from the noise. And poker is full of this quiet faith. A bluff may fail tonight but still be correct. A fold may feel painful but save you over time. A disciplined call may lose now but remain profitable across thousands of similar situations. In each case, the immediate feeling can be misleading. This is what makes poker such a hauntingly honest game. It does not flatter the ego. It does not always reward virtue quickly. It simply reveals, over time, whether your way of thinking aligns with the hidden mathematics of reality. And that is perhaps the deeper lesson of expected value. That wisdom is not always visible in the moment. Sometimes it looks like loss. Sometimes it feels like uncertainty. Sometimes it passes through disappointment before it can become truth. To play poker well is to slowly accept this. To understand that one hand means almost nothing, and yet every hand matters. That each decision is a small vote cast into the future. And though any single vote may seem insignificant, together they shape the world you eventually inhabit. A good poker player is not someone who wins every hand. That person does not exist. A good poker player is someone who keeps making decisions that would still be good if the hand could be played forever. And perhaps that is one of the calmest and most unsettling truths mathematics has to offer, that the right path is not always the one that feels good immediately. Sometimes it is simply the one that remains beautiful when repeated across time. And from that quiet idea, another question begins to emerge. If expected value teaches us what is worth doing over the long run, then how do we measure whether a risk is worth taking in the first place? To answer that, we have to move deeper into the mathematics of thresholds, where every chip placed into the pot becomes a question about cost, chance, and the invisible price of hope. Every poker hand contains a quiet question. Sometimes it arrives dramatically, with a large bet and a long silence. Sometimes it appears almost invisibly, hidden inside a small decision that seems too ordinary to matter. But whether the moment feels intense or trivial, the question remains the same. Is this uncertainty worth the price? That is what poker asks over and over again. And the mathematics that helps answer this question lives in what players call pot odds, equity, and thresholds. These words may sound technical at first, but beneath them lies something surprisingly simple and almost philosophical. Poker is constantly asking you to compare what something costs with what it might become. And in that sense, poker is not only about cards, it is about value under uncertainty. It is about deciding when to continue, when to retreat, and when hope itself is mathematically justified. Imagine a simple scene. The pot is growing. Your opponent bets. You look down at your hand and realize you are not currently winning, but you might improve. Perhaps you hold 4 cards to a flush. Perhaps you have an open-ended straight draw, where one of several cards could complete your hand. You are suspended in that beautiful and uncomfortable space between weakness and possibility. Now the question becomes not, do I want to win? Of course you do. The real question is, how much should I be willing to pay for the chance? This is where pot odds enters the picture. Pot odds is simply the relationship between the size of the bet you must call and the amount of money already sitting in the pot. In other words, it tells you the price the game is offering you. If the pot contains 100 chips and your opponent bets 50, then you must call 50 to try to win a total of 150. That ratio matters. It creates a threshold. It tells you how often your call must succeed in order to be worth it over time. This is one of the most elegant things about poker mathematics. It turns vague emotional hope into measurable structure. Without mathematics, a player might say, I have a feeling this could work. With mathematics, the player asks, does the price justify the possibility? That shift is subtle, but profound, because poker is not asking whether you might get there. Almost anything might happen. A single card can always appear. The real question is whether the chance of it happening is large enough to make the risk worthwhile. This is where the concept of equity becomes important. Equity in poker means your share of the pot based on how likely you are to win if all remaining cards were dealt. If you have a hand that will win about 1 time in 4, then you have roughly 25% equity. If your hand will win about 1 time in 2, then you have about 50% equity. Equity is your hidden ownership of the future. You do not possess the pot yet, but probability says some portion of it already belongs to you in principle, and that is a beautiful idea. Because equity is not certainty, it is not possession, it is not reward in your hand. It is possibility with weight, a kind of invisible claim on what might be. Poker lives inside that invisible claim. If your equity is greater than the price you are being asked to pay, then the call may be mathematically correct. If your equity is lower, then however tempting the moment feels, the mathematics begins to whisper that this hope is too expensive. This is what a threshold really is. A threshold is the line between a risk that is sustainable and a risk that quietly drains you over time. And in poker, those thresholds are everywhere. Should you call this river bet? Should you chase this flush draw? Should you defend your blind? Should you continue with a weak pair on a dangerous board? Each decision has its own invisible boundary. Cross it too often in the wrong direction, and your stack begins to dissolve, not all at once, but gently, steadily, almost imperceptibly. That is one of the eerie truths of poker. Most mistakes do not feel like disasters when they happen. They feel reasonable. They feel hopeful. They feel emotionally understandable. And that is exactly why they are dangerous. Because poker punishes not only recklessness, but also beautifully justified self-deception. A player might say, "It was only one more call." And often, that is how the mathematics of loss works, not through dramatic collapse, but through a long series of tiny overpayments for uncertain dreams. There is something almost existential about this. Because life too is full of risk thresholds. How much time should you invest in something uncertain? How much emotional energy should you give to a possibility that may never arrive? How long should you continue when the signs are unclear? How much should you pay in effort or hope or attention for the chance that something beautiful might still happen? Poker compresses all of these questions into chips and cards. It gives uncertainty a visible price, and then it asks you to decide whether the future is worth buying. This is why strong poker players are often not the boldest people at the table. They are often the most selective. They understand that courage is not always pressing forward. Sometimes courage is folding. Sometimes wisdom is the ability to let go of a possibility, not because it is impossible, but because it is too expensive. That distinction matters deeply. A bad fold can cost opportunity. A bad call can cost structure. And poker is always balancing those two losses against each other. This is what makes the game so psychologically rich. Every threshold contains tension between mathematics and desire. The numbers may say one thing, the heart may say another. And in the pause before a decision, those two forces meet. The chips wait, the cards remain hidden. And somewhere in that silence, you are asked to choose not only what you think will happen, but what kind of uncertainty you are willing to live with. There is another quiet beauty here as well. Thresholds teach restraint. They remind us that not every possibility deserves pursuit. Not every draw deserves investment. Not every flicker of hope should be fed. Some futures are too mathematically fragile to chase. And there is peace in knowing that, because once you understand thresholds, you no longer need to be seduced by every maybe. You begin to see that discipline is not pessimism. It is simply the art of preserving yourself for better opportunities. Poker rewards that kind of patience. It rewards the ability to distinguish between a beautiful possibility and a profitable one. And those are not always the same thing. In the end, risk thresholds reveal one of the quietest truths in the mathematics of poker. Not all hope is equal. Some hope is supported by structure. Some hope is only longing, wearing the mask of probability. To play well is to learn the difference, to feel the invisible line where risk becomes too costly, to know when the future is worth paying for, and when it is time to release it back into the unknown. And once that becomes clear, another shadow appears at the edge of the table. Because if mathematics can tell us when to call honestly, it can also tell us when to bet dishonestly. And that is where poker becomes even stranger. Poker is a game of hidden landscapes. It is not only about what is visible on the table, but also about the invisible lines that stretch between players' minds. These lines are often subtle, intangible, and yet rigorously structured. One of the most fascinating mathematical aspects of this hidden landscape is the geometry of the bluff. A bluff is, at its core, an act of controlled illusion. You represent a hand you do not hold, projecting strength, weakness, or indecision. But unlike an arbitrary lie, a bluff is measured. It is constrained by mathematics. It must respect pot size, betting history, the tendencies of your opponent, and the hidden probabilities of what hands remain in play. It is, in essence, a geometric structure that exists in time, space, and probability simultaneously. Consider a simple geometric metaphor. Imagine a triangle. At each corner, there is a value: your actual hand strength, the potential hands your opponent might hold, and the pot odds available. The bluff exists at a point inside that triangle. Its position is determined by how these three values interact. Move too close to one corner and the bluff becomes obvious. Move too far and it collapses entirely. There is a delicate equilibrium, a balance point where risk, deception, and potential reward intersect. This is not merely theory. Every bluff can be described in terms of probability thresholds. If you are representing a strong hand when the board suggests weakness, the likelihood of success depends on how many plausible hands your opponent could have that beat you. If the board is coordinated, connecting many straights and flushes, your bluff must occupy a smaller, more precise space. If the board is disconnected, barren of coordinated cards, the bluff can expand, covering a broader range of possibilities. Mathematicians sometimes call this concept expected value of deception. A successful bluff increases your expected value because it converts a zero or negative situation into a profitable one. But the geometry is delicate. Each decision point, the size of the bet, the position at the table, the opponent's tendencies, is a dimension in a multi-layered geometric space. The bluff is not linear. It curves around perception, folds through probability, and intersects with timing. Now imagine the multidimensional geometry when multiple players are involved. A bluff directed at one opponent must be reconsidered in light of potential calls from another. It is no longer a single triangle but a complex polyhedron, each face representing a potential reaction. Every additional player adds dimensions. Every additional layer of betting history tilts the shape further. Even the smallest detail matters. How long you pause before betting, how much you hesitate, how your stack interacts with the pot, all of these adjust the angles of the bluff in this invisible space. In a sense, poker players are quietly sculpting multidimensional figures with nothing but perception, risk, and mathematics as their tools. Bluff geometry also teaches a paradoxical lesson. The strongest bluffs are often the simplest. The bluff does not need to be complicated to be effective. Its elegance lies in positioning, timing, and proportion. A bet that is too large may push all opponents away, making it profitable, but reducing the opportunity for future gains. A bet that is too small may encourage a call that defeats the bluff. The exact balance is often subtle, invisible, yet mathematically calculable. This is why great players speak of fold equity. Fold equity is the probability that an opponent will fold given the bluff, multiplied by the size of the pot. It is a numerical expression of influence, a measure of how successfully your bluff bends reality to your will. And like all mathematics in poker, it exists in tension with the unknown. You cannot know your opponent's exact decision, only estimate it, and those estimates, layered with the combinatorial space of potential hands, create a geometric field that is as much art as it is science. The geometry of bluffing becomes even more fascinating when we consider repeated interactions. Patterns emerge over time. Opponents detect tendencies. Angles of deception must shift. The bluff is no longer static. It becomes a dynamic shape, stretching, compressing, and rotating through the invisible mathematical space of your opponent's perception. In this sense, bluff geometry is almost like quantum mechanics. The act of observing changes the system. A player who has been folded to repeatedly adjusts. The bluff that succeeds once may fail twice, and each time the shape of the decision space alters slightly. Even human psychology can be translated into this geometric language. Fear, caution, aggression, all these become vectors in the multidimensional space. A conservative opponent constrains your angles, shrinking the effective area of successful bluffing. A loose, aggressive opponent expands it. To bluff successfully is to navigate this dynamic, psychological geometry while respecting the hard mathematics of probability, pot odds, and combinatorial possibility. And there is a hidden serenity in this. The bluff, for all its deception, obeys rules. It is not chaos. It is a system. It is structured. And within that structure, there is beauty. The act of bluffing becomes a meditation on influence, perception, and probability. You are not merely betting. You are shaping a mathematical space that exists as much in the mind of your opponent as on the felt surface of the table. Perhaps the most haunting truth of bluff geometry is that it always exists between two extremes. Between truth and deception. Between risk and reward. Between the visible and the hidden. Every successful bluff occupies a narrow corridor of possibility, balanced carefully between these extremes. Step outside, and the bluff collapses. Step inside, and the world bends, just slightly, toward your intention. Bluff geometry, then, is both art and science. It is mathematics realized in social space. It is a study of lines, planes, and multi-dimensional angles that exist entirely in perception, constrained by combinatorial reality. It is a delicate structure where patience, calculation, and intuition meet, and when it succeeds, it transforms uncertainty into control, chaos into elegance, and risk into silent mastery. Poker is not only a game of cards, chips, and timing. It is a game of belief, of conjecture, of what might be true given what you already know. And nowhere is this more mathematically rich than in Bayesian thinking. Named after the 18th century mathematician Thomas Bayes, Bayesian reasoning offers a framework for updating knowledge in a world of uncertainty. In poker, it transforms vague suspicion into a structured way of navigating hidden realities. At its core, Bayesian thinking is simple to state, even if its implications are profound. It says this: whenever you gain new information, you should revise your beliefs about the world. Nothing is fixed. Everything is provisional. Each new card, each bet, each hesitation, each raise is a signal. And each signal should adjust the probability of what is true. Imagine you are facing a player in late position. You have observed their tendencies over many hands. Perhaps they play tightly, rarely entering pots without strong holdings. Perhaps they are aggressive, willing to push chips with a wide variety of hands. Now, they make a substantial bet. What does this mean about the hand they hold? In classical probability, you might consider the strength of the hand in isolation. In Bayesian reasoning, you consider it relative to your prior beliefs about the player's behavior. You ask, given what I already know, how should my belief about their hand change? If they have been tight so far, a large bet is more likely to indicate strength. If they have been loose, the same bet might indicate a bluff. Bayesian reasoning is recursive. Your prior belief, or prior probability, interacts with the new evidence to create a posterior belief, the updated estimate of reality. This posterior becomes the new foundation for the next decision. Every observation folds into the next, creating a continuous chain of updated probabilities. Poker, unlike many games, unfolds in real time, so this updating is happening constantly, silently, beneath the surface of every decision. Consider a practical example. Suppose you are holding 4 cards to a flush on the turn. You estimate that your opponent has a top pair roughly 50% of the time, and a drawing hand the remaining 50%. They make a bet that is half the size of the pot. That bet is evidence. It is information. You adjust your estimate. Perhaps the half-pot bet is more common among drawing hands. You recalculate the probability that they will beat your hand if the flush does not complete. This is the power of Bayesian thinking. It does not demand certainty. It does not promise a crystal ball. It simply says, use what you know to refine what you think is true. And in poker, where uncertainty is absolute and luck can obscure clarity, this refinement is the closest thing you can have to control. Bayesian reasoning also allows you to integrate multiple sources of information simultaneously. Consider a multi-way pot. Each opponent's actions must be combined with your understanding of their tendencies, the visible board, and the implied odds of future bets. Each piece of evidence shifts the balance. A player who has been bluffing frequently changes the probability distribution of their hand range. A player who suddenly slows down may be signaling a trap. Every observation nudges the posterior probability in subtle ways. The mathematics behind this is elegant. Bayes' theorem states that the probability of a hypothesis given evidence is equal to the probability of the evidence given the hypothesis, multiplied by the prior probability, divided by the probability of the evidence. In plain language, it asks, how likely is this observation if my assumption about reality is correct, adjusted by what I previously believed, normalized across all possibilities? It is a quiet, disciplined calculation, one that can be performed in seconds, almost subconsciously, by experienced players. Bayesian thinking in poker has profound psychological implications. It encourages humility. It teaches that every belief is provisional and that certainty is a dangerous illusion. A player who relies solely on intuition, ignoring the need to update their beliefs in response to evidence, will eventually be exploited. Conversely, a player who is rigorous in updating their beliefs, even imperfectly, aligns their perception with reality more closely, giving them a long-term advantage. Another remarkable feature of Bayesian reasoning is its flexibility. It can be applied to situations with extremely limited data. Even a single bet or a single unusual action can shift the posterior probability. Bayesian players know that every card revealed, every movement and every timing pattern is information. It does not have to be overwhelming. Each small piece accumulates. Over the course of a session or many sessions, these updates converge, producing a rich, dynamic understanding of the table. The recursive nature of Bayesian thinking also introduces a subtle tension between knowledge and uncertainty. A posterior belief is never final. It is always provisional, awaiting the next observation. Every new card, every new bet, every new signal can challenge your understanding. In that sense, Bayesian thinking mirrors life itself. We are constantly revising beliefs based on evidence, yet absolute certainty is rarely possible. Poker crystallizes this human condition into a tangible and mathematically precise form. Bayesian reasoning also illuminates the concept of reverse engineering an opponent's logic. By observing behavior and applying Bayesian updates, a player can infer not only the probability of specific hands, but also the strategies and tendencies underlying an opponent's decisions. It becomes a recursive thought experiment. You consider what your opponent believes about you, how they update those beliefs, and how those updates influence their actions. Each layer adds a dimension, a subtlety, a hidden structure to the game. Finally, Bayesian thinking in poker is inseparable from patience. Posterior probabilities do not always align with immediate results. A player might fold a hand that looks strong in isolation because the Bayesian update reveals that, given all evidence, the risk exceeds the reward. Another player might call a marginal hand because the updated probabilities favor continuation in the long run. Success is not measured by a single outcome, but by alignment with the hidden mathematics of the table. In this way, Bayesian thinking transforms poker from a simple game of luck into a meditation on uncertainty, evidence, and rational belief. It trains the mind to see the invisible structures beneath action, to interpret signs with care, and to remain humble in the face of incomplete information. Each decision is no longer a guess. It is an informed estimate, a refined perception, a probabilistic claim about what is true. As the cards continue to fall and the chips continue to move, the Bayesian mind constantly adjusts, one observation at a time, one update after another. The player carves a path through the uncertainty, and in that path, the mathematics of belief intersects with human psychology, perception, and intuition, creating a landscape that is at once rigorous, fluid, and quietly hypnotic. Poker is not merely a game of chance or probability. It is a game of interaction, a dance between minds. And the mathematics that governs this interaction belongs to a field known as game theory. At first glance, game theory may sound abstract, distant, or intimidating. But at its core, it is surprisingly human. It is the mathematics of decision-making when outcomes depend not only on chance, but also on the choices of others. In poker, this creates a silent, intricate battlefield where every action contains both strategy and consequence. Game theory asks a simple question. Given that your opponent is also making rational choices, what should you do to maximize your long-term advantage? In other words, how do you act when your success depends not only on your own cards, but also on the hidden intentions and calculations of others? This is a profound shift in perspective. Most games, and indeed much of everyday life, can be approached as isolated problems. I make a decision, I see a result, I adjust. But poker is different. Every decision resonates. Every bet sends ripples through the possible actions of your opponents, which in turn shapes your next decision, and so on, in a recursive, self-referential loop. One of the most illuminating concepts in game theory is the Nash equilibrium, named after the mathematician John Nash. In simple terms, a Nash equilibrium occurs when all players have chosen strategies such that no one can improve their expected outcome by unilaterally changing their strategy. The players are, in a sense, perfectly balanced. No action is strictly better than another, because each choice has already been optimized relative to the choices of others. Imagine a situation at the poker table. You are in a late position with a marginal hand. Your opponent has been aggressive but predictable. How should you act? If you are a rational player and your opponent is rational as well, the Nash equilibrium provides a guideline, a mixed strategy, where you sometimes fold, sometimes call, and sometimes raise, in proportions that prevent your opponent from exploiting your tendencies. It is not a fixed pattern but a probabilistic approach, designed to maintain balance across repeated interactions. This is where poker becomes fascinating. Unlike a simple coin flip or a single hand, poker is iterative. Strategies unfold over time. A purely rational equilibrium is rarely reached in practice because human psychology intervenes. Fear, greed, intuition, and deception all affect decisions. Yet game theory gives a framework for understanding how these deviations create opportunities. By recognizing the equilibrium and then observing departures from it, a skilled player can exploit patterns and gain advantage, all while respecting the underlying structure of optimal play. The mathematics of game theory also introduces the concept of zero-sum dynamics. In a zero-sum game, one player's gain is precisely another player's loss. Poker, in its simplest form, is zero-sum. The chips you win are exactly equal to the chips someone else loses. This forces each decision to be measured not in isolation but in relation to all other players' potential responses. Every bet is an argument, a proposal, a claim on the shared resources of the table, and every call, fold, or raise is a counter-argument. The game becomes a continuous negotiation where mathematical reasoning and psychological insight intertwine. A remarkable feature of game theory is its treatment of mixed strategies. Whereas traditional reasoning might suggest that a player should always act the same way in a given situation, game theory demonstrates that unpredictability is itself optimal. If you always fold with a weak hand and always call with a strong one, your opponents can exploit you. But if you randomize your actions according to calculated probabilities, you become less exploitable. The mathematics ensures that your uncertainty is itself a strategic asset. This leads to one of the most subtle and counterintuitive lessons of poker. Optimal play is not about always winning each individual hand. It is about maintaining a structure that maximizes expected value over time while minimizing vulnerability. Victory is not measured in immediate outcomes, but in resilience and consistency, in the silent mathematics that balances probability, psychology, and strategic interaction. Game theory also teaches a quiet humility. You can never be certain of your opponent's hand. You can only estimate ranges, observe tendencies, and update beliefs. Even perfect logic cannot guarantee success in a single instance, because the human element introduces noise. Yet by embracing the principles of equilibrium and rational strategy, you create a framework that protects you from long-term exploitation. Over time, adherence to these principles translates into sustainable advantage. Another profound aspect is iterated games, where decisions in one hand influence future hands. Players develop reputations, signal tendencies, and respond to patterns over time. A bluff today may influence a fold tomorrow. A pass in one round can shape perception in a later round. Game theory formalizes this idea. Optimal strategies must consider not only the immediate situation, but the evolving network of interactions. The mathematics becomes temporal, layered, and dynamic. Even subtle nuances, such as position of the table, stack sizes, and betting sequences, can be understood through the lens of game theory. Each variable shifts the equilibrium slightly, creating new strategic opportunities. Small adjustments grounded in mathematical reasoning can amplify expected value over many iterations. The game becomes not only a contest of cards, but a study of structure, balance, and anticipation. Game theory also frames deception as a rational choice. Bluffing, for example, is not merely psychological manipulation. It is a mathematically informed strategy designed to shift the equilibrium in your favor. A well-timed bluff introduces uncertainty into your opponent's calculations, forcing them to adjust their probabilities and, in doing so, creating opportunities for profit. The geometry of perception and the mathematics of interaction converge in a single decision. Ultimately, game theory elevates poker from a simple game into a meditation on interdependent strategy and the mathematics of human interaction. Every bet is a statement, every fold is a concession, and every call is a measured act of calculation. The table becomes a living network of probabilities, tendencies, and equilibria, continuously evolving with each new card and each new action. Through game theory, poker reveals itself not just as entertainment, but as a reflection of rationality under uncertainty. It is a disciplined negotiation with chance, a structured interaction among minds, and a silent dialogue between mathematics and psychology. The mathematics does not guarantee victory, but it provides a framework to navigate complexity, anticipate consequences, and act optimally, even when the outcome is unknown. In poker, position is everything. It is one of the quietest, yet most mathematically potent forces in the game. Many beginners overlook it, focusing instead on the cards they hold, the size of the pot, or the drama of a single hand. Yet, the position of a player at the table fundamentally shapes every calculation, every decision, and every strategic possibility. It is the invisible lens through which all probability, risk, and opportunity are refracted. To understand positional power, imagine the table as a clock. Each player sits at a different hour. The dealer position, often called the button, moves clockwise after every hand. The positions immediately after the blinds act first, while those later, particularly the dealer, act last. Acting last provides an informational advantage. It allows a player to observe the actions of others before committing to their own choice. And in a game governed by probability, timing, and hidden information, that is invaluable. From a mathematical perspective, positional power is about information asymmetry. Every action your opponents take reveals partial information about their likely holdings. If you act before them, you have less data, and your decisions are based more heavily on prior probabilities, intuition, or estimation. If you act later, you incorporate more evidence, updating your beliefs about what they hold. Acting last effectively gives you an extended Bayesian update before every choice, a refined view of the hidden reality in front of you. Consider a hand where you hold a marginal pair. If you are first to act, you must rely on the combinatorial probability of your opponent's range of hands. If you act last, however, you can see who bets, who checks, and who raises. Each of these observations shifts the expected value of continuing the hand. Your risk thresholds, your potential bluffing opportunities, and even your implied odds are recalculated in real time. In other words, position magnifies your mathematical control over the unfolding game. Positional power also interacts with pot geometry. Acting later allows you to choose bet sizing with more precision. You can manipulate the pot to maximize expected value or minimize exposure. For example, a small bet in position may entice a marginal hand to call, increasing your potential profit. A large bet may force folds when your goal is to protect a vulnerable holding. Acting out of position, by contrast, often forces rigid decision-making, constrained by limited information and the probabilistic uncertainty of unobserved opponent actions. The power of position is cumulative. In a multi-way pot, each action from each player updates your posterior probability estimates. Acting last allows you to synthesize this entire sequence of evidence before committing. Acting first reduces the accuracy of your decision tree, leaving your choices more vulnerable to variance. Over time, these small advantages compound, yielding a subtle yet measurable edge. Position is not a single event. It is a framework for every decision across every hand. Mathematically, positional power can be visualized as a vector field. Each player's potential actions create forces that push and pull on your expected outcomes. Acting later allows you to integrate these vectors, adjusting direction and magnitude based on the observed landscape. Acting earlier leaves you projecting vectors into the unknown, a noisier, less reliable calculation. The vector analogy captures the dynamic, continuously updating nature of decision-making in poker, where probability flows through the table and every position shapes the trajectory of potential outcomes. Moreover, position affects strategic flexibility. When acting last, you can execute complex plays that combine bluffing, value betting, and pot control with minimal risk. You can adjust your strategy to exploit tendencies revealed by earlier actions. Acting first limits these options. The same strategic choices become more rigid, more exposed, and more predictable. Position essentially multiplies the degrees of freedom available to a mathematically minded player, turning every hand into a richer landscape of opportunity. There is also a psychological dimension to positional power. Players acting later can apply pressure more effectively, inducing mistakes from those acting earlier. The earlier players are making decisions with incomplete information, often feeling subtly coerced into folding or committing chips under the influence of uncertainty. Acting last amplifies your ability to manipulate perception, leveraging both mathematics and human behavior to create advantage. In practical terms, strong players often choose starting hands based on position. Marginal holdings are playable in late position, where the informational advantage compensates for their weakness. Conversely, the same holdings are often folded in early position to avoid being forced into difficult decisions with insufficient data. The mathematics of probability, equity, and expected value interact seamlessly with positional awareness, dictating the optimal range of actions. The interplay between position and bluffing is particularly fascinating. A bluff executed in late position has a higher likelihood of success because it exploits the reduced informational advantage of opponents who acted earlier. The geometry of perception bends toward you, creating angles of deception that are mathematically favorable. Acting out of position compresses these angles, limiting bluffing opportunities and increasing the risk of being called or raised. Positional power also shapes long-term strategy. Over many hands, consistently exploiting position creates a compounding edge. It affects stack management, risk allocation, and the calculation of implied odds. The mathematics of incremental advantage operates silently, accumulating small gains that eventually translate into significant results. Position is not just a tool for a single hand. It is a foundational principle that governs the rhythm of play across an entire session. In essence, positional power turns the table into a structured system where time and order become critical variables. Acting last transforms uncertainty into information, elevates probability into actionable insight, and allows strategy to unfold with precision. It is a mathematical lever that magnifies every calculation, every bluff, and every risk assessment. And yet, positional power is subtle. It does not guarantee a win on any given hand. It does not eliminate variance. It simply shifts the expected value in your favor, providing the mathematical foundation upon which skill, observation, and discipline can build long-term success. Like many concepts in poker, it rewards patience, understanding, and respect for the hidden structures that govern the game. Poker is a game of uncertainty, but it is also a game of perception. The cards are dealt randomly. The shuffle creates a sequence beyond prediction, and yet human minds are wired to see patterns, meaning, and intention, even in chaos. This tension between the true randomness of the deck and the illusion of order is one of the most fascinating aspects of poker, and the mathematics that underpins it helps us navigate the delicate interplay between probability expectation and human psychology. At first glance, randomness seems simple. Each card in a shuffled deck has an equal chance of appearing in any position. If you draw a single card, there is a 1 in 52 probability that it will be any particular card. For two cards, the combinations grow exponentially, 1 in 52 multiplied by 1 in 51, and so on. The mathematics of combinatorics, the counting of possibilities, shows that the potential sequences in a standard 52-card deck are staggeringly large, far exceeding the number of seconds in the age of the universe. Yet the human mind struggles to internalize this scale. We expect patterns, repetitions, and cycles, even when they are statistically impossible. This is where the illusion of randomness begins. When a card appears that seems too lucky or too unlucky, our brains tend to infer intention or design. A series of red cards in a row might feel suspicious, even though, mathematically, a run of consecutive outcomes is entirely probable in a random sequence. The gambler's fallacy is one expression of this illusion. The belief that after a streak of hearts, a spade is due. In reality, each card remains independent. Probability does not remember history, yet the illusion persists, shaping perception, decisions, and emotional responses at the table. Poker players who understand this illusion gain an advantage. By recognizing that sequences are governed by combinatorial mathematics rather than narrative expectation, they can avoid overreacting to streaks or patterns. This is not merely academic, it has practical consequences. For instance, if an opponent has won 3 large pots in a row, it may feel like a hot streak, but mathematically, the probability of independent outcomes does not favor a 4th victory. A Bayesian mind updates its beliefs based on prior tendencies rather than perceived luck, distinguishing genuine skill from perceived patterns. The illusion of randomness also extends to human behavior. Opponents may believe their actions are unpredictable, but in reality, patterns often emerge unconsciously. Mathematical analysis of betting sequences, timing, and frequency can reveal structure hidden beneath apparent chaos. Observing these patterns allows a player to transform the apparent randomness of human behavior into a calculable probability distribution, bridging the gap between chance and strategy. Consider the shuffle itself. Even the most thorough shuffle cannot eliminate certain statistical properties. Card clumps, sequences, and distributions arise naturally. Mathematics predicts these tendencies. A truly random sequence may still produce clusters, runs, and apparent coincidences. Understanding that these phenomena are expected, not suspicious, allows a player to remain psychologically stable while observing the unfolding game. Randomness also interacts with combinatorial space. The number of possible hands, the sequences of flop, turn, and river, and the branching possibilities of betting rounds create an almost infinite network of potential outcomes. Yet each outcome, when observed in isolation, can feel meaningful. A player who has folded to 3 consecutive bluffs may perceive a narrative of unlucky timing, while mathematically each event is independent, each probability self-contained. Recognizing this distinction is crucial for disciplined decision-making. Mathematically, randomness can be described through probability distributions. In poker, the uniform distribution governs the deck. Each card is equally likely at the start, but as hands are dealt and the deck shrinks, conditional probabilities emerge. A player who observes exposed cards can update their calculations, understanding the likelihood of remaining cards in play. The combination of true randomness and conditional probability forms the invisible mathematics that governs every decision. The illusion of randomness also influences bluffing. Opponents may perceive patterns where none exist, creating opportunities for strategic manipulation. A player can exploit cognitive biases using perceived streaks, timing anomalies, or irregular betting sequences to induce folds or miscalculations. This creates a fascinating interplay. The mathematical randomness of the deck contrasts with the perceived randomness of behavior, and the skilled player navigates both simultaneously. There is also a philosophical dimension to randomness in poker. The game presents a universe where outcomes are uncertain, yet governed by strict probabilistic laws. Each hand is a microcosm of chance, demonstrating the limits of prediction and the necessity of probabilistic thinking. The illusion of randomness reminds us that our perception is limited, and that disciplined observation, mathematical reasoning, and psychological insight are required to navigate complexity. Even the emotions at the table are shaped by perceived randomness. Players often attribute intentionality to luck, seeing agency where none exists. Wins feel deserved, losses feel cruel. Understanding the mathematics of probability allows a player to detach emotionally, seeing each outcome as a discrete, independent event. This creates mental clarity, reduces tilt, and aligns decisions with expected value rather than fleeting perception. Finally, randomness is central to the long-term structure of poker. Short-term variance is extreme. Even statistically optimal plays may lose hands due to the inherent uncertainty of the game. Mathematics provides the lens to interpret this variance. By understanding probability, combinatorial possibilities, and conditional outcomes, players can maintain perspective, focusing on long-term expected value rather than the misleading stories of individual hands. The illusion of randomness, then, is both a challenge and a tool. It challenges perception, introducing cognitive traps, biases, and emotional reactions. But it also offers opportunity. Understanding the difference between true chance and perceived pattern allows strategic clarity, psychological control, and mathematically informed play. Every hand, every shuffle, every decision is a dance along the edge of order and chaos, where human perception meets the cold certainty of probability. Poker is a game that balances on the knife edge between skill and chance. Even the most disciplined, mathematically precise player cannot escape the inherent fluctuations in outcomes caused by probability. This is the phenomenon we call variance, the storm that sweeps through every session, every hand, and every decision. To understand poker fully, one must not only understand expected value, combinatorial space, or positional power, but also the unpredictable turbulence of variance and how it shapes the perception and reality of the game. Variance is, in essence, the measure of deviation from the expected outcome. If you know that a hand has an expected value of 5 chips, that does not mean you will gain exactly 5 chips each time. You might win 20 in one instance, lose 10 in another, and break even occasionally. Over many iterations, the average aligns with expectation, but the individual outcomes fluctuate wildly. These fluctuations are the storm, invisible yet relentless, that every poker player navigates. Imagine the mathematical landscape of poker as a calm ocean at first glance. Expected value calculations, probability distributions, and Bayesian updates form the underlying currents. Yet, the surface is never calm. Random shuffles, unexpected bluffs, and unpredictable opponent behavior create waves and gusts that can overwhelm even the most precise calculations. The mathematics of variance quantifies these fluctuations, but it cannot eliminate them. It provides a framework for understanding, not a shield against unpredictability. Variance interacts deeply with the concepts we have explored: combinatorial space, randomness, Bayesian thinking, and game theory. Even if your strategy is perfectly balanced, if you are acting in accordance with optimal mixed strategies, variance will still produce streaks of losses or wins that feel paradoxical. A hand with a positive expected value can lose multiple times in succession. A weak hand may occasionally win spectacularly. The mathematics ensures long-term profitability, but short-term perception can feel chaotic, disorienting, even unfair. This storm is not merely a practical challenge, it is also a psychological one. Players may react emotionally to sequences of bad outcomes, a phenomenon known as tilt. Tilt distorts probability assessment, exaggerates risk, and undermines strategy. Understanding variance is the first step in mastering emotional control. Recognizing that swings are natural, mathematically inevitable, and temporary allows the player to maintain calm, make rational decisions, and avoid compounding losses. Consider a series of hands in which your expected value calculations suggest a slow, steady gain of 10 chips per 100 hands. In reality, you may encounter a stretch where you lose 20 chips, then gain 30, then lose 10 again. Each fluctuation is a random deviation within the mathematical framework of probability. Over thousands of hands, the law of large numbers ensures alignment with expectation, but each moment remains unpredictable. Variance is also a measure of risk. The greater the potential outcomes, the larger the storm. Aggressive strategies with high variance can lead to spectacular gains, but also sudden and significant losses. Conservative strategies reduce the amplitude of the storm, offering more stable short-term results, but often at the cost of lower long-term expected value. The mathematics of risk versus reward becomes tangible here. Each decision is a trade-off between the height of potential waves and the strength of the vessel navigating them. Mathematically, variance is the square of the standard deviation, a measure of how far outcomes deviate from the mean. In poker, it represents the range of possible results around your expected value. A single hand with an expected gain of 5 chips may fluctuate anywhere from -50 to +50, depending on the combinatorial possibilities, the opponent's tendencies, and the random order of the deck. Across multiple hands, these deviations form a pattern, a statistical storm whose intensity depends on both the inherent randomness of the game and the style of play. Variance also interacts with perception. Human minds are pattern-seeking machines. When a losing streak occurs, it may feel as though the universe is conspiring against you, even though mathematically it is simply a series of independent events aligning temporarily in a negative direction. Conversely, a sudden winning streak can create overconfidence, prompting a player to overestimate skill or underestimate risk. The mathematics remains unchanged, yet the illusion of control or chaos can profoundly influence behavior. One of the most subtle aspects of variance is its temporal dimension. Short-term outcomes can fluctuate dramatically, but over time, expected value dominates. A mathematically sound player recognizes this and adapts their focus to the long horizon. Variance is the storm in the moment. Expected value is the compass guiding the journey. By maintaining discipline, players ride the waves without being capsized by temporary turbulence. Variance also influences strategic adjustments. A player experiencing a long streak of bad luck may need to reevaluate aggression, pot control, and hand selection, not because their strategy is flawed, but because short-term deviation can distort perception and encourage suboptimal decisions. The mathematics of expected value does not change, but the mental framework must account for the storm, incorporating both probability and psychology into decision-making. Furthermore, variance is inseparable from bankroll management, the mathematics of sustainability. Even the most statistically advantageous strategy can fail disastrously if the player cannot absorb the natural fluctuations of the game. Maintaining an appropriate reserve of chips relative to bet size and expected volatility ensures survival through the storm. In essence, understanding variance allows a player to endure temporary chaos while remaining aligned with long-term mathematical advantage. High variance hands, such as bluffing, drawing to a flush, or making speculative plays, create the most dramatic turbulence. Low variance hands, like value betting strong hands in position, produce smoother outcomes. Skilled players choose when to embrace volatility and when to minimize exposure, navigating the storm with awareness of its amplitude, frequency, and impact. The mathematics of variance also interacts with probability distributions. The more extreme the potential outcomes, the wider the distribution, the stronger the storm. Each bet, each fold, each call adjusts the shape of this distribution. Experienced players visualize these ranges, understanding not only the expected value, but the likely deviations. The storm is mapped, measured, and respected. Ultimately, variance teaches a profound lesson. Uncertainty is inherent, inevitable, and mathematically quantifiable. Poker is a microcosm of life in this sense. No strategy, no calculation, no prediction can eliminate randomness, but by understanding the statistical nature of deviation, by observing patterns without being fooled by illusions, by embracing long-term expected value over short-term outcomes, a player can navigate the storm rather than be destroyed by it. Variance is both challenge and teacher. It sharpens perception, tests discipline, and illuminates the interplay between probability, psychology, and strategy. It reminds us that the mathematics of poker is not simply about outcomes, but about processes, the continual calculation of risk, reward, and uncertainty. It is the storm that ensures the game remains dynamic, unpredictable, and endlessly fascinating. Poker is a game of cards, chips, and probability, but it is also a game of the mind. While mathematics governs expected value, combinatorial possibilities, and optimal strategies, human psychology shapes every decision in ways that often defy logic. Understanding the traps created by the mind is as essential as understanding the mathematics of the deck. These psychology traps can turn mathematically advantageous situations into costly mistakes, or conversely create opportunities for the observant and disciplined player. The first and most pervasive trap is the illusion of control. Humans have a natural tendency to overestimate their influence over random events. In poker, this manifests as the belief that one's skill can overcome the inherent variability of the game. A player might perceive a streak of wins as evidence of superior ability or a streak of losses as a personal failing. In reality, the mathematics of probability ensures that short-term fluctuations, variance, will often dominate outcomes. Recognizing that control is probabilistic rather than absolute allows players to maintain composure and make rational, mathematically informed decisions. Closely related is the gambler's fallacy, the false belief that past events influence independent probabilities. A sequence of losses or wins may feel like it should balance out, but each hand, each shuffle, and each deal is independent. The probability of drawing a specific card does not change based on prior outcomes. A disciplined player applies combinatorial reasoning rather than intuition, understanding that runs of luck, positive or negative, are natural within the mathematics of randomness. Another common trap is confirmation bias. Players notice patterns that support their existing beliefs while ignoring evidence that contradicts them. For example, if you believe an opponent bluffs frequently, you may interpret ambiguous actions as bluffs, even when the hand strength does not support it. This bias distorts Bayesian updating. Proper mathematical reasoning requires integrating all evidence objectively, calculating posterior probabilities without privileging data that simply reinforces prior assumptions. Loss aversion is also a potent trap. Humans feel losses more intensely than equivalent gains. In poker, this leads to overly conservative play after losing hands or over-aggression in attempts to recover losses, often called chasing. The mathematics of expected value demonstrates that each hand should be evaluated independently, based on probabilities, potential gains, and risk thresholds, not emotional desire to recoup previous losses. Recognizing loss aversion allows the player to adhere to long-term strategy rather than momentary impulses. Overconfidence functions as the opposite trap. Winning hands or successful bluffs can inflate perception of skill, leading to unnecessary risk-taking. A player riding a winning streak may deviate from optimal strategy, overestimating the likelihood of future success. Mathematically, each hand retains its independent expected value. No amount of prior wins alters probability. Overconfidence can increase variance exposure and reduce alignment with mathematically optimal decisions. Timing and behavior introduce another set of traps: pattern projection and tells. Humans often unconsciously create signals through posture, chip handling, or timing. Opponents may perceive these as intentional, reading them as evidence of strength or weakness. Yet the mathematics of probability dictates that these signals are often unreliable unless confirmed through consistent observation. Disciplined players separate random behaviors from statistically meaningful patterns, updating their Bayesian estimates only when evidence supports it. Tilt, a state of emotional disturbance caused by frustration, anger, or fatigue, is another critical psychological trap. Tilt leads to suboptimal decision-making, misjudged bluffs, incorrect pot control, and ignoring risk thresholds. Even mathematically sound strategies fail when executed under tilt. Understanding variance, expected value, and probability provides a framework to recognize tilt early, allowing a player to pause, recalibrate, and re-engage with clarity. The illusion of streaks also affects perception. Humans naturally seek narratives. 3 consecutive winning hands may feel like skill, 3 losses like misfortune. Mathematically, short-term sequences are meaningless relative to long-term expected value. Successful players internalize this, focusing on process over immediate results. Bayesian updates allow them to integrate observed tendencies while separating the statistical noise of variance. Another subtle trap is anchoring. Players often fixate on a previous hand, bet, or outcome when making current decisions. For example, if an opponent previously bluffed successfully, a player might assume the next action is also a bluff, regardless of probability and evidence. Anchoring distorts calculations, shifting expected value estimations. Correct practice involves re-evaluating each situation independently, while integrating all relevant information, consistent with combinatorial reasoning and Bayesian updates. Psychology traps also arise from social dynamics. Table image, reputation, and interpersonal perception influence decisions. A player perceived as loose may face frequent folds when betting, while a tight image may invite bluffs. Mathematics and probability remain constant, yet perception creates opportunities and vulnerabilities. Skilled players leverage this by adjusting strategies, exploiting cognitive biases in opponents, while maintaining mathematically optimal play themselves. Bluffing itself interacts with psychology traps. A bluff succeeds not because the hand is strong, but because it exploits perceived probability and behavioral biases. Understanding the interplay between true probability and the opponent's psychological perception transforms bluffing from chance to strategy. Mathematics informs the likelihood of success, while psychology informs the choice of target and timing. Decision fatigue is another invisible trap. Over the course of many hands, mental energy wanes, impairing calculation and probability assessment. Mistakes increase as a result of cognitive overload, leading to suboptimal plays. Variance can exacerbate this effect. A series of losses may accelerate tilt. A series of wins may induce overconfidence. Understanding this interaction allows a player to pace themselves, ensuring alignment with expected value and probability calculations across sessions. The subtlety of psychology traps is that they are invisible until they manifest in behavior. A mathematically rigorous player must constantly monitor both self and opponents. Each deviation from probability-informed reasoning, each emotional impulse, and each perceptual bias is an opportunity for exploitation or a hazard to avoid. Recognizing these traps transforms poker from a reactive game into a reflective, disciplined practice. Poker is not only a game of probability and psychology, it is a game of choice. Every hand, every bet, and every fold branches into a network of possibilities, a complex structure that mathematicians call a decision tree. These trees are not merely diagrams, they are living representations of potential outcomes, risk, and reward, unfolding with each action. Understanding them allows a player to navigate the game with clarity, balancing strategy, mathematics, and intuition. At its simplest, a decision tree begins with the hand you are dealt. From there, each potential action fold, call, raise creates a branch, which itself branches into subsequent possibilities determined by opponent reactions, the next cards revealed, and future betting rounds. As you move deeper into the tree, the branches multiply rapidly. The mathematics of combinatorial expansion becomes immediately apparent. Even with just a few actions, the total number of possible paths through a hand can exceed hundreds or thousands. Visualizing this helps one understand why poker is simultaneously simple and infinitely complex. Each small decision opens a vast landscape of potential outcomes. Decision trees also provide a framework for evaluating expected value at each node. Every branch represents not only a possible sequence of actions, but also a weighted probability of outcomes. By multiplying the likelihood of each path by its potential gain or loss, a player can calculate which branches maximize expected value. This is where mathematics and strategy converge. Understanding the combinatorial complexity of the tree allows for rational, disciplined decisions rather than guesses or impulsive choices. The mathematics of pruning is also essential in decision trees. Not every branch is equally relevant. Some possibilities are dominated by others. They offer lower expected value or introduce unnecessary risk. Mathematicians call this pruning, the removal of suboptimal branches, simplifying the tree without losing strategic insight. In poker, pruning helps the player focus on meaningful options, marginal bluffs, optimal folds, and profitable calls, while ignoring improbable or dominated paths. This reduces cognitive load and increases efficiency in decision-making. Bayesian updates integrate seamlessly into decision trees. Each observation an opponent's bet size, timing, or previous behavior reshapes the probability assigned to each branch. A player acting in position constantly updates beliefs about likely opponent holdings, effectively recalculating the expected value of every branch in real time. The tree is dynamic, evolving with every new piece of information, and mastery comes from recognizing how to navigate it fluidly rather than rigidly. The branching structure also illustrates risk versus reward. Some paths offer high potential gain but low probability, while others offer smaller, safer outcomes with higher likelihood. The mathematics of variance becomes apparent here. The shape of the decision tree reflects not just expected value, but the volatility of potential outcomes. A skilled player weighs both aspects, selecting branches that optimize long-term profitability while controlling short-term exposure to variance. Decision trees also reveal the hidden power of position. Acting later in the sequence allows a player to see which branches have been traversed by opponents, effectively collapsing uncertainty for that round. Early action requires choosing paths without this advantage, increasing reliance on prior probability and general strategy. Position transforms the structure of the tree, magnifying control for later actors while constraining the decision space for earlier ones. Bluffing introduces an additional layer of complexity. A bluff is a deliberate branch into a probabilistic path that may mislead opponents and alter the evolution of the tree. If the bluff is successful, it collapses multiple opponent branches into suboptimal choices, creating favorable outcomes. If called, it introduces negative outcomes but can be evaluated within the broader expected value framework, showing that even failure is a calculable risk. The mathematics of mixed strategies from game theory applies directly. Randomization across branches can make actions less exploitable. Decision trees also illuminate the impact of stack size and betting structure. Each branch carries potential consequences not only in immediate gains, but in future strategic options. A large stack allows exploration of riskier branches, while a small stack limits flexibility. Understanding how each branch interacts with chip distribution adds depth to both planning and execution. The combinatorial structure of the tree must be contextualized with these practical constraints. Another dimension is opponent modeling. Each player has their own decision tree, and your choices interact with theirs. Optimal play requires not just evaluating your own paths, but anticipating which branches your opponents are likely to take. This creates a layered network of trees, a recursive structure where one player's probability assignments influence the next. Mathematics provides tools to estimate these interactions, while observation and psychology inform practical application. Iterated decisions reinforce the complexity of the tree. Poker is rarely one isolated hand. It is a series of interconnected events. Earlier choices influence opponent perception and subsequent branch likelihoods. A consistent pattern of aggression may prune opponent branches toward folding, while passivity may expand their decision space. Over time, the tree is not static. It evolves as history accumulates, creating a dynamic landscape of strategy and probability. Visualizing decision trees also aids in understanding the geometry of choice. Each node is a point of potential, each branch a trajectory through the space of probability. Choices are vectors in this space, and optimal navigation requires considering direction, magnitude, and interaction with other vectors. Mathematics allows players to quantify these relationships, turning intuition into structured reasoning. Decision trees also clarify pot control. By evaluating each branch with respect to the size of the pot, the potential risk, and the implied odds of drawing, players can make rational sizing decisions that influence the shape of future paths. This strategic leverage is an extension of both combinatorial reasoning and expected value calculations, demonstrating how the abstract mathematics of the tree translates into practical, actionable decisions. The complexity of decision trees also underscores the importance of simplification. While theoretically, a full analysis would include every possible sequence, human cognition cannot manage such exponential growth. Pruning dominated paths, focusing on high probability branches, and updating beliefs with Bayesian logic allows a player to navigate effectively without losing mathematical rigor. The tree becomes a tool for clarity rather than an overwhelming burden. Poker tournaments transform the familiar dynamics of cash games into a crucible of strategy, endurance, and mathematics. Unlike cash games, where chips represent a fixed monetary value, Tournament chips are markers of survival. Losing all your chips eliminates you. Winning them progresses you. And the ultimate goal is not simply to maximize expected value per hand, but to navigate a complex structure of risk, probability, and opponent behavior to survive and thrive. Understanding tournament survival requires the integration of combinatorial mathematics, expected value, variance, and psychological insight into a single continuous framework. The mathematics of tournament survival begins with stack size, which directly influences both risk tolerance and strategic options. Early in a tournament, deep stacks allow for flexibility, enabling speculative plays, calculated bluffs, and aggressive exploitation of opponents' tendencies. Here, combinatorial considerations dominate. The number of possible hand sequences and betting paths is vast, and each decision must balance probability of success against potential chip loss. Deep stack mathematics permits exploration of high variance strategies without immediate danger of elimination. As the tournament progresses, short stacks impose constraints. When chip count approaches critical thresholds, such as the minimum required to call a bet, the median stack at the table, or the average stack in late stages risk assessment shifts dramatically. A hand with positive expected value in isolation may be unplayable if losing it would eliminate the player. Mathematics still governs the probabilities of winning or losing, but survival introduces conditional thresholds. Expected value must now be evaluated not only in chips, but in terms of tournament life, a probabilistic measure of elimination risk. The independent chip model, or ICM, formalizes this relationship. ICM calculates the monetary value of a player's stack relative to others, considering payout structures and survival probabilities. Mathematically, it transforms chip counts into expected monetary outcomes, weighting decisions by the probability of advancing through the prize structure. A fold may sometimes be more valuable than a mathematically profitable all-in call, simply because preserving chips increases the likelihood of reaching higher payouts. Understanding ICM requires translating combinatorial possibilities, probabilities of hand outcomes, and opponent behavior into a single coherent framework. Variance plays a central role in tournaments, particularly when stack sizes differ significantly. A high variance play, such as pushing all in with a speculative hand, may dramatically alter your position relative to others. The mathematics of combinatorial space predicts the likelihood of success, but short-term randomness. The variance storm can override expectation. Recognizing when variance is an asset and when it is a threat is critical. Aggressive plays may exploit opponents' fear of elimination, while conservative strategy may preserve survival through high variance stretches. Bubble dynamics exemplify these principles. The bubble occurs when one elimination away from a significant payout, creating pressure on all remaining players. Mathematically, chip preservation is more valuable than marginal expected value. Plays because the cost of elimination is catastrophic relative to potential gains. Combinatorial and probability calculations continue to guide play, but the weight of survival amplifies the importance of risk management, positional awareness, and opponent tendencies. Position remains crucial. Acting later in a hand provides information that collapses some branches of the decision tree. Observing others' actions allows a player to adjust betting, folding, or bluffing strategies with reduced uncertainty. This is magnified in tournament play, where chip preservation amplifies the value of informed decisions. Mathematics dictates probabilities, combinatorics, and expected outcomes, while observation and timing convert these into actionable strategy. Psychology is also magnified in tournament contexts. Short-stacked players often display desperation, overvaluing speculative hands or overestimating fold equity. Deep-stacked players may exert pressure, forcing marginal folds or inducing risk-laden plays. Understanding these tendencies allows mathematically informed exploitation of opponents' biases. Bayesian thinking updates probabilities based on observed behavior, while decision trees illustrate the branching outcomes influenced by stack sizes, position, and psychological dynamics. Implied odds gain new significance in tournaments. The potential to accumulate chips in future hands, building a stack that ensures survival or allows aggressive flexibility alters present decision-making. Calculating implied value involves estimating both combinatorial hand possibilities and opponent tendencies, projecting the likelihood of winning not only the current pot, but subsequent pots. The mathematics of expectation, probability, and variance converge with strategy to guide long-term survival. Tournament survival also requires careful bankroll management within the game itself. Each hand carries a probability distribution of chip gain or loss. Comprehending the full spectrum of outcomes weighted by likelihood informs decisions that prioritize maintaining a viable stack over maximizing short-term gains. The mathematics of combinatorial possibilities and expected value must be tempered by survival thresholds, opponent behavior, and variance considerations. The metagame in tournaments adds another layer. Opponents' perceptions of your style influence their decision trees. Aggressive behavior may induce folds in short-stacked opponents, while conservative play may invite bluffs from overconfident players. Calculating optimal responses requires integrating combinatorial mathematics, probability theory, expected value, and psychological modeling into a coherent approach. Late-stage tournaments amplify these dynamics. The blinds increase, forcing action even in marginal situations. Risk thresholds shrink, variance effects dominate, and survival calculations become intertwined with positional leverage and psychological pressure. Every decision must balance the mathematics of probability, combinatorial space, and expected value against the immediate threat of elimination. The interplay between short-term randomness and long-term strategy is more pronounced than at any other point. Mathematics also clarifies ICM pressure situations, where chip utility diverges from chip quantity. A call with strong expected value in chips may have negative ICM value due to elimination risk. Survival requires translating chip probabilities into expected monetary value within the payout structure, often pruning theoretically profitable branches to preserve life. Decision trees must incorporate not just combinatorial hand outcomes, but the conditional probabilities of survival and elimination, making the tournament game tree far more nuanced than cash game analogs. Psychology, again, intertwines with mathematics. Players adjust to perceived aggression, tendencies toward tilt, or desperation near critical thresholds. Bayesian reasoning allows continuous updates of opponent models, while expected value calculations incorporate these observations to guide optimal survival strategies. The integration of human behavior into combinatorial probability is both subtle and powerful. Tournament survival also emphasizes adaptability. Early strategies suitable for deep stacks may become catastrophic under bubble pressure or short stack conditions. Mathematics guides the transformation. Combinatorial possibilities, expected value, variance, and probability remain constants, but risk thresholds, survival weightings, and psychological modeling must adapt continuously. The skilled player recognizes this, navigating dynamic environments with disciplined flexibility. In poker, the stack is more than a collection of chips. It is a representation of strategic flexibility, potential, and survival. Every decision, from calling a small bet to committing all chips, interacts with the size of your stack, the distribution of opponents' stacks, and the underlying mathematics of probability and combinatorial outcomes. Understanding stack mathematics is crucial for navigating both cash games and tournaments, and for transforming abstract calculations into practical decisions at the table. At its core, stack mathematics is about relative leverage. A deep stack allows exploration of high-variance strategies. You can speculate with suited connectors, float with positional advantage, and execute calculated bluffs, knowing that a loss does not threaten survival. In contrast, a short stack imposes constraints. Each bet becomes high stakes, each decision critical, and each deviation from optimal expected value carries disproportionate consequences. Mathematics quantifies this relationship. Larger stacks reduce relative risk, allowing the probability distributions of outcomes to play out over multiple iterations, while small stacks magnify variance, compressing the range of safe options. Stack size also interacts with bet sizing. A bet of 1/10 your stack has a different impact depending on your total chips. Expected value calculations incorporate both the size of the potential gain or loss and the probability of each outcome. but the effect on your future options, your leverage, in subsequent hands must also be considered. Each chip carries not just monetary value but strategic weight, which mathematics allows us to quantify and optimize. The concept of effective stack is essential. When two players face each other, the smaller of the two stacks effectively limits the potential betting in that hand. This constrains decision trees, pruning branches that exceed the effective stack. A mathematically rigorous player evaluates hands not just in isolation, but in context of effective stacks, adjusting expected value calculations and risk thresholds accordingly. Combinatorial possibilities remain constant, but the probability space contracts when stack limitations are imposed. ICM implications extend stack mathematics beyond simple chip counts. In tournaments, chip utility is non-linear. The difference between 10,000 and 20,000 chips is not equivalent to the difference between 20,000 and 30,000 chips. Mathematics formalizes this using models that weight chip counts by survival probability and payout structure. A mathematically optimal decision may sometimes involve folding a hand with positive chip expected value if the survival adjusted expected value ICM value is negative. Stack mathematics, therefore, becomes an exercise in conditional probability and expected utility rather than raw arithmetic. Stack ratios also shape risk tolerance. Deep stacks can absorb high variance plays because the probability of ruin is low. Shallow stacks require conservative approaches to avoid elimination. Even when expected value calculations suggest marginal profit, variance interacts with stack size in a precise mathematical relationship. As stack-to-blind ratios decrease, the relative magnitude of potential deviation from expectation increases, making risk management essential. A mathematically minded player quantifies this relationship, balancing aggression and caution to optimize survival and growth. Position magnifies the importance of stack mathematics. Acting later allows observation of how much opponents commit to the pot relative to their stacks, informing conditional probabilities of hand strength and potential outcomes. Combinatorial reasoning and Bayesian updates converge. Each branch of the decision tree is weighted not only by hand probabilities, but also by the constraints imposed by stack sizes. This dynamic interplay shapes strategic options and expected value calculations. Stack mathematics also informs all-in decisions. The decision to commit all chips depends on probability of winning the hand, potential gain relative to stack size, and tournament or game context. Mathematically, an all-in represents a branch of the decision tree where variance is maximized. The range of outcomes spans from total loss to total gain. A skilled player evaluates the combinatorial possibilities of opponent hands, calculates the expected value, and factors in survival thresholds and implied odds before committing. Another dimension is chip preservation versus accumulation. Deep stacks allow the player to accumulate chips gradually, exploiting opportunities to extract value from opponents over multiple rounds. Short stacks must prioritize preservation, sometimes folding mathematically profitable hands to maintain a viable stack. This trade-off is a function of combinatorial space, expected value, and variance. Preserving chips reduces the probability of ruin, while accumulating chips enhances long-term leverage. Stack mathematics also intersects with psychological factors. Players adjust their behavior based on perceived stack advantage or disadvantage. Deep stack players can pressure smaller stacks, forcing suboptimal folds or inducing errors. Conversely, short stacks may gamble with marginal hands to escape survival pressure. Mathematics quantifies these pressures. Conditional probabilities, expected value, and variance models predict likely responses, allowing strategic exploitation of both self and opponents. Effective stack management also relies on probabilistic foresight. Each hand affects not only immediate expected value, but the structure of future decisions. Calculating the likelihood of surviving several rounds requires integrating variance, probability distributions, and potential betting sequences. Mathematically, this is a multi-layered expected value calculation. The present hand is evaluated in the context of future opportunities, which are themselves probabilistic and dependent on current outcomes. Combinatorial considerations also guide bet sizing strategy relative to stack. A pot-sized bet has different implications for a shallow versus deep stack. The probability of committing a significant portion of one's chips alters expected value calculations and affects the branching structure of decision trees. Mathematics provides a framework for evaluating each path, allowing the player to optimize bets in a way that balances risk, potential reward, and survival probability. Stack mathematics also illuminates bluffing potential. Bluffing requires committing chips to force opponent folds. The success probability of a bluff, combined with the size of the bet relative to stack, determines expected value. Small stacks may lack leverage to execute effective bluffs, while deep stacks can pressure opponents with probabilistically calculated bets. Bayesian updating informs whether the opponent is likely to fold, integrating observed tendencies into mathematical reasoning. Tournament and cash game dynamics differ, but stack mathematics remains constant in principle. The underlying combinatorial space, probability distributions, expected value calculations, and variance considerations do not change. Only the interpretation shifts. In tournaments, survival is paramount, and ICM-adjusted value guides decisions. In cash games, chips are fungible, and raw expected value calculations dominate. In both cases, understanding the interaction between stack size, probability, and combinatorial outcomes allows rational, disciplined decision-making. Poker is a game of probability, psychology, and strategy, yet the flow of time adds an often invisible but powerful variable. Every hand carries not only combinatorial complexity and expected value considerations, but also the constraints of decision-making under time pressure. Whether in live games with limited seconds per action or online tournaments with countdown clocks, time-shaped strategy influences risk assessment and interacts with mathematics in subtle ways. Understanding how time pressure affects decisions allows players to navigate the game more effectively, converting potential panic into calculated efficiency. Time pressure first manifests through cognitive load. Each decision in poker requires evaluating multiple factors: the cards you hold, the combinatorial possibilities of opponent hands, the expected value of potential actions, risk thresholds, implied odds, position, stack sizes, and psychological tendencies. When time is constrained, the brain must simplify these calculations. Mathematically, this is analogous to pruning a decision tree. Low probability branches are ignored and calculations rely on heuristics rather than exhaustive enumeration. While this can lead to mistakes, it is also an opportunity to develop intuitive understanding, where repeated exposure to probability distributions allows quick, accurate estimation without formal calculation. Time pressure also amplifies the impact of variance. Rapid decisions may lead to marginal errors that, over many hands, influence outcomes. Consider a simple probability calculation. If a player must decide whether to call with a hand that has a 35% chance of winning a pot worth 10 big blinds, taking extra time might allow careful computation of combinatorial possibilities and pot odds. Under time pressure, the player may misestimate the probability, slightly underweighting expected value. Mathematically, even small errors compound over multiple rounds, demonstrating how decision speed interacts with probability and variance. Expected value under time constraints requires a balance between accuracy and speed. Some branches of the decision tree can be simplified without significant loss of precision. For example, hands that are clearly dominant or clearly dominant require minimal calculation. Marginal hands, however, may suffer under pressure as the subtle differences in probability distributions are harder to evaluate quickly. Experienced players develop mental shortcuts, relying on pattern recognition and combinatorial intuition to approximate expected value. Psychology interacts strongly with time pressure. Rapid decision-making increases the likelihood of tilt or impulsive play. Emotional responses, fear of losing, or overconfidence can distort probability estimation and expected value calculations. Mathematics provides a framework for evaluating choices objectively, but under time pressure, the mind may default to bias or heuristic reasoning. Understanding the interaction between cognition, psychology, and probability helps players recognize when intuition aligns with mathematics and when it diverges. Time pressure also affects bluffing and deception. The speed of decision can itself convey information. Opponents may interpret rapid actions as strength or weakness, attempting to assign probabilities to hand strength based on timing tells. Mathematically, timing is a variable that can influence the opponent's expected value calculations, creating opportunities to manipulate perception through deliberate pace. Bayesian reasoning becomes relevant. Each observed timing behavior updates the probability estimate for the opponent's likely holdings and strategies. Position magnifies the effect of time pressure. Acting first in a hand requires commitment without information, relying solely on probability and combinatorial evaluation. Acting later allows observation of prior actions, reducing uncertainty. Under time pressure, the benefit of acting last can be even more pronounced, as later players can collapse multiple decision tree branches based on opponent behavior. Mathematics provides the foundation to quantify expected value, but time constraints influence which branches are realistically considered. Stack size interacts with time pressure in critical ways. Deep stacks allow more flexibility in rapid decisions, since potential errors carry less immediate risk relative to the total chip count. Short stacks, however, magnify the impact of mistakes. A miscalculated call under time pressure could lead to elimination, even if the decision was mathematically marginal. Decision-making under these conditions requires awareness of both combinatorial probabilities and survival thresholds, blending stack mathematics with temporal strategy. Time pressure also changes risk thresholds. Players under constraints may become risk-averse, folding hands that are mathematically profitable, or risk-seeking, overcommitting due to fear of time running out. Both deviations from optimal expected value highlight the importance of mental discipline. Mathematics quantifies the trade-off between potential reward and probability of success, but time pressure introduces variance in human execution. Recognizing this effect allows players to adjust, either by practicing rapid evaluation or by managing the pace strategically. The combinatorial explosion inherent in poker becomes more difficult to navigate under time constraints. Each hand can branch into hundreds or thousands of potential sequences. Calculating precise probabilities for all outcomes is impossible in a few seconds, so players rely on mental approximations. Experienced individuals internalize combinatorial relationships, such as the number of ways to complete a flush or a straight, and translate them into rapid decision rules. This mental modeling allows accurate expected value assessment without formal enumeration. Bayesian updates are also impacted. Each observed action by opponents ideally informs the probability of their holdings. Under time pressure, these updates may be incomplete or inaccurate, leading to suboptimal choices. Mathematics still governs the underlying probabilities, but human execution under constraints introduces noise into the model. Recognizing this interaction allows strategic adjustment. Sometimes conservative plays reduce the effect of potential errors, while calculated aggression exploits opponents' likely misestimation. Time pressure interacts with tournament structure in unique ways. Increasing blinds and escalating decision demands compress optimal time allocation. Early rounds allow deliberation. Late rounds, particularly during the bubble or pay jumps, impose high-stakes rapid calculation. Mathematically, the same combinatorial, probability, and expected value principles apply, but temporal constraints amplify the consequences of mistakes. The player must adapt both cognitively and strategically to maintain long-term expected value and survival probability. Decision trees under time pressure become heuristic-guided. Rather than considering every branch, players prioritize high-impact nodes, dominant hands, likely bluffs, and pot-controlling sequences. Pruning low-probability branches simplifies calculation, enabling rapid decisions while preserving alignment with expected value. Mathematics ensures that pruning does not distort strategy significantly, but intuition and experience guide which branches are considered negligible. Time pressure also magnifies psychological traps, including loss aversion, overconfidence, and tilt. Rapidly reacting to previous outcomes may bias probability assessments, leading to deviations from optimal expected value. Mathematics provides an objective framework, but human execution under temporal constraints introduces variability. Recognizing the interaction of emotion, time, and probability allows a player to implement mental checks, pacing strategies, and pre-computed heuristics to mitigate errors. Bluff geometry is subtly influenced by time. Quick bluffs may appear more credible or less thought out, depending on opponents' perceptions. Mathematics predicts the expected value of a bluff based on fold probabilities, pot size, and stack ratio, but the psychological effect of timing adds an additional variable. Bayesian thinking allows integration of this information. Observed reactions update the probability of bluff success, influencing the decision tree even under rapid conditions. Randomness perception is also distorted under pressure. Players may see patterns where none exist, overreacting to recent hands or short-term variance. Mathematics reminds the player that probability remains constant, but temporal constraints increase the likelihood of heuristic-driven errors. Recognizing this allows disciplined navigation of combinatorial space and preservation of expected value, even when the clock ticks down. Time pressure also interacts with meta strategy. Experienced players can manipulate opponents by varying decision speed, deliberate pauses, or rapid actions, all to perceived strength. These manipulations influence opponent behavior, effectively reshaping their decision trees. Mathematics, combinatorics, and Bayesian updates allow quantification of likely responses, converting temporal dynamics into strategic advantage.